Excellent. Well, yeah, let's get started. We've got pretty much critical mass here, and so it's today we've got Mick Bowman. The slides are up here. So Mick is director of the Sawtooth platform. Is that correct?
Of blockchain research.
Blockchain research. Yeah. Thanks, Mick. Let me pass it over to you.
Okay, so I'm just going to talk about one of the research projects we have going on right now. It's called Private Data Objects. When I started this 4 years ago, started working on blockchain stuff, Intel was kind of looking for what's the connection between blockchain and Intel hardware features. And one of the things that we were just developing at the time was the software guard extensions, or SGX, which is a trusted execution environment. So a lot of our focus has been on how to replace a lot of the very public and transparent and inefficient computations that currently occur in kind of blockchain and smart contract systems with much more efficient and confidentiality preserving computations that could happen inside these trusted execution environments. And so that's basically what we're going to talk about on it. So private data objects is really, there's really two parts of it. So if you think about a kind of what you would traditionally get with something like in a smart contract system like Ethereum, the contracts are actually executed in the validator, and they're sort of executed on chain. So all of the validators are executing all the contracts, and we'll come back to that in a minute and the problems that that causes in a minute. So one of the things that we've been able to do is to separate contract execution from the actual blockchain and the ledger. And we'll talk a little bit more about the benefits of that, but it really creates great opportunities for improvements in performance and efficiency and confidentiality, data management policies, and the rest. So the one piece is related to execution of these privacy-preserving smart contracts. And the idea behind these is that all data associated with the contract is encrypted so long as it's outside of one of these trusted execution environments. And then the trusted execution environment prevents any other application or individual from looking at the contents of the data. In particular, SGX makes it so that even the owner of the machine can't see the stuff that's happening inside the enclave that way. So it gives us a safe environment where we can execute code on otherwise encrypted data, which means that we can define these really nice kind of access policies for data, and these access policies kind of stick with the data no matter where it moves. So if I give you a database right now and I say, you know, we've got this license, I'm going to give you access to this data, there's nothing that prevents you from turning around and giving that data to another party. And the idea behind these private data objects is that the access controls stick with the data so that I can give you access to this file, but you can't turn around and give it to somebody else as well. So we get some fairly sophisticated sort of access and update policies that we can implement. We get confidentiality of the data, and we get stickiness of these policies that are associated with the data as it moves around. The ledger then, so that's really sort of the smart contract and the behavior side of things. What the ledger then does is it gives us a way of kind of establishing authority of the particular version of the smart contract that's sitting off on the side. So we get an audible record of commitments. The commitments don't actually contain any of the data in the smart contract. They simply record a transition of the state from one to another. So we can audit that record, we can verify the correctness of the transactions that are taking place and the updates that are taking place, but we don't expose any of the information about what's happening. The blockchain ensures integrity, so it makes sure that there is always at most one authoritative instance of an object unless the policies of the object allow there to be more instances. And that integrity policy is enforced by the ledger. And then the final thing, which is a little less important for today, is the ledger allows us to do coordination. So if you've ever done sort of database transactions and you know we only want to commit the update of the database if all n of these updates were taking place successfully. And the blockchain allows us to do this sort of atomic cross contract updates that way. So just to bring this home and make it fairly concrete, one of our customers who is a three-letter car company came to us and asked us to start looking at some of these, to address some of these problems that are related to sort of changes in the sense of vehicle ownership. So in the US, we buy a car and we own that car for 3 years or 5 years or 10 years, depending on how long you want for it. But in many places, there's been a very strong transition to these notions of short-term leases. You can think in the US of things like Zipcars, or other kinds of ride-sharing techniques for it. And the problem is that the insurance company has no way of putting together a realistic, verifiable profile for the drivers, given that the drivers are moving back and forth amongst all of these vehicles. None of that information then is reported back to the insurance company. So drivers are paying high premiums because they have to be rated at essentially the highest risk category because there's no information about it. Similarly, the insurance companies are moving to these kinds of meter services that, sort of a pay by mile, very short-term commitment to it. And so what we were looking for, what this company was looking for, was something that would allow them to do verifiable and representative logs of driver history over all of the vehicles that the driver used. Some notion of being able to do rapid evaluation that would allow fully personalized quotes. So it could be targeted to you specifically as a driver based on past history of your driving, potentially in different kinds of vehicles as well. And at the same time, obviously, because the privacy restrictions in the EU, and in particular all the GDPR work, none of the personal information that's collected about the individual can be exposed for inappropriate access at any point in time. So just to give you a sort of a comparison for in the US place, there's little dongles that you can now put in your car from your insurance company that tracks your information. One of the insurance companies allows you to get this dongle, creates a profile for you, and you ship the dongle back to them, and then they give you a rate quote based on the characteristics of your driving. And that profile, first off, they get access to all of the information that's been collected about you. And second is every insurance company has to get it. And so we'd like to make this both private and more broadly applicable. And what the PDOs allow us to do is to create these contracts where we can ensure that we can verify the integrity of the car that's generating the information. We can verify its connection to the driver. All of that data then about the trips that the driver makes, no matter what car they're in, can go into their profile. Now, here's the interesting thing about it is, this profile would be lovely. The driver sort of owns it. But if the driver has the right to change it and modify it, then its value is completely lost. So the smart contract enforces, even on its owner, a limitation on its ability to modify the data that's inside that profile. So what we get out of that is the profile represents a high integrity representation for the driver. The insurance companies can create a contract that does rating of the drivers. We're able to connect the driver profile and the rating contract through a secure channel so that the driver profile information is never exposed. The driver gets to decide which contracts it wants to rate him or her. And then at the end, the driver gets to decide whether the insurance company gets to see whether the information, whether the rating should be exposed to the insurance company that way. So we get high integrity on the driver profile. We get control over our own data. We don't get the right to do anything with it, but we get the right to see who sees it. We get to protect the privacy of the information, privacy and confidentiality of the information that's being passed back and forth as well. So the insurance company gets what they want. They get a high integrity, very dynamic quote. Driver gets what he or she wants in the control of their information, um, we meet all of the requirements for the privacy protection as well. And so these are the kinds of things that we're building with it. I'll talk about another one's more relevant to the smart cities in a minute. So then just I'm going to dive into technical stuff for just a second, because these techniques are important, but you got to understand the context in which sort of the smart contracts execute today and why the sort of SGX-based or trusted execution environment-based approach is so important. So smart contracts today, basically, the way Ethereum works is in order to verify the output of the contract, we ship the contract execution to all of the validators in the system. They all execute it simultaneously, and then they kind of vote on the correct result. And as long as they all compute the same thing, or as long as enough of them compute the same thing, then we accept that computation, we commit it, and we move on to the next one. I mean, the problem with that is that, you know, every validator has to see every contract, which means that they have the visibility into it, so we don't get any privacy or confidentiality. It's really slow because of the inefficient, or because of the sort of redundancy that's in the computation, and really inefficient for doing that. And just to give you a concrete number for the inefficiency, so Ethereum right now is running about between 20 and 25,000 validators in the Ethereum, full validators in the Ethereum network. One of the most popular smart contracts in Ethereum right now is this thing called CryptoKitties, which is like a digital Tamagotchi. And the CryptoKitties are lovely, except that because of the way that the contracts work, every operation you perform in your CryptoKitty is essentially being operated simultaneously on 25,000 nodes. So as much as I like the CryptoKitties and think they're awesome and cool, I don't need 25,000 servers worth of redundancy in order to execute that operation. So that's the typical way for doing it right now. When we do it with SGX and these trusted execution environments, because we're essentially putting trust in the integrity of the compute environment, independent of any of the sort of human operations that are a part of it, it means that we can greatly reduce the redundancy that's required and still get similar kinds of resiliency to attacks. So we replace the redundancy with kind of a chain of attestations. And it means that we can update one of these smart contracts one time in one enclave. It generates a proof of correctness, which is then handed off to the ledger, and the ledger verifies the proof of correctness that way. And then they accept the update. So the effect of that is that we get off-chain execution. So we get privacy from data isolation. We get privacy and confidentiality from the trusted execution environment itself. So even the hosts of the computation don't get to see what's happening inside the contract. It's really efficient. We really only need, and there are reasons why, but we're using very small amounts of redundancy in order to get resiliency that's comparable to what you would get from a larger network. And it scales in the sense that because of the separation from contract execution and ledger, if we add more compute, we get more contracts that can be executed. And that's very different than what you would get from your traditional implementation of smart contracts. So then just mapping that back to the private data objects work, we're just basically taking one of these smart contracts, executing it inside the enclave. The enclave generates these proof of correctness, and the ledger then assures that the updates are serialized correctly. It means the ledger doesn't need contractor state, so this addresses a lot of our sort of physical access to data. So the GDPR issues we're able to address very clearly with this. Performance impact is minimal on smart contract execution, so we get much better performance and performance scales. And one of the other things that's interesting about this approach is that because we don't have to do, we don't have multiple systems computing the same thing and voting on the answer, it means we can actually relax some of the determinism characteristics that go along with existing smart contracts. This is really important for IoT based applications, where you don't necessarily have all of the data, where everyone doesn't get exactly the same data for it. So this is a real strength for it. just sort of going back then to kind of the what it's good for. As I mentioned before, the contract state is always encrypted outside the enclave. So the owner does not get to the contract owner does not get to see the data unless the contract allows for it to happen. And I'll give you an example of why this is really critical here in a minute. And there's a number of policies that this facilitates construction, right? So we talk a lot about when we're talking about privacy preserving data access, we talk a lot about differential privacy and the techniques for building differential privacy. This is a good technique and it does exactly what we want in many ways. The problem is that the owner of the data is the one that's sort of solely responsible for setting up the policies for the data. With these private data objects, what we can do is we can have the data itself enforce differential privacy access to it. So that means that we can have policies that are enforced even on the, I'll say in air quotes, the owner of the data. This means also, because of the way that the contract works, that we can show compliance to certain sets of characteristics of the data or the operations. And so we can do bids on contracts where the one who's offering the bid can guarantee the confidentiality of the contract. We can do constrained access on analysis of video data. So video data can come in, but we can guarantee that only the computation that we've agreed we would perform on it will ever be performed on it. You can't do these sort of secondary computations on it, which might violate the privacy principles of it. This also applies when we're doing things like doing normalization of genomic databases, where the database represents something that is a critical intellectual property. We want to do cross-company computations on that genomic data, but we don't want to violate the intellectual property rights of the companies that are providing it. We could do automated data aging. That is, to be clear, I can give you a policy that will guarantee that it will delete the data after a certain time period that way. And then the regular things that we've talked about before with blockchains, we can do multi-party and confidential audits on information as well. Okay, so let me just stop for a minute. Questions?
How do you, how does the, I don't want to go into any specific details, but the SGX itself is able to, it's built into the chip, right? So it's able to enforce. Is that, how do you ensure that somebody can't pretend to be SGX? That's really the question.
So I'll give you the very short, high-level answer. If you want the long, detailed answer, we can also have that conversation, but I would suggest we not do it on this call. Okay. The short answer is that when the chip is created, there's a registration process that happens. It generates its own set of public key, private key pairs during the initial burn-in. The public key that's associated with that is immediately registered with the attestation service. And so we have a list of the Intel Attestation Service has a list of the public keys of the processors that have been created. And there are ways that we can do this so that we can never map the public ID back to a private ID, but something that's signed with a private key can be verified to have come from an enclave. So there's a unique key pair that's burned into the hardware initially, and there's a registration process for that before it even leaves the factory.
Got you. So the private key is effectively burned into the silicon at manufacture time.
Correct.
Private key is registered. How do you know that that's
like I said, by the way, that is a grossly oversimplified description of it.
Totally get it. Right. I'm really looking for the mechanism and where it can really be relied on. And if so it sounds like you can do this without effectively requiring Intel to be a trusted entity the keys, the public keys are all public. Anybody can have access to them, and nobody has a list of the private keys.
That is exactly the way it works. So there's basically the first level of attestation is that yes, this is an Intel hardware with certain characteristics, right? That's really the only thing that Intel is in the business of doing. This is a piece of hardware. It was manufactured with these characteristics, and we can verify those characteristics.
Gotcha.
Of the physical machine. Right? Then the actual the management of the keys and the signing and the management of the attestation from the hardware, you can either use the attestation service we provide, or you can build your own. It's entirely up to you.
Are you putting that into IoT devices too? Are you putting that into low-cost, small devices so as you could effectively attest data at the edge?
At this point, no. I would say that there are comparable capabilities from ARM with TrustZone. It doesn't have quite the same attestation, and the characteristics are a little different. But TrustZone was designed for like point-of-sale systems to be able to protect the information on payment systems. That's really what it was designed for. And you could leverage some of those capabilities on smaller low-end devices and connect them to the higher-end compute in your gateways or your processing systems.
So there's a way to make SGX and TrustZone interoperable?
It's just basically how you write the application on top of it. There's no specific set of standards for how to do it.
Okay, no, that's excellent. That was what I was looking for. And
yeah, and we've had these conversations frequently about what an application might look like. Obviously, we're not in that business, so we're not building the code for it. But we have some reasonable idea of what those applications would look like.
So, just for what we're trying to do here, obviously, what we'd like to do is to make sure that that a particular technology is not required, but that if the right technology is delivered, then you can get better security, or you can, that the base concepts are supportive of differentiated technology.
Yeah, and I think that's kind of the approach that we've been taking with it. That you can run smart. We know how to do smart contracts, right? We know how to do it. We know how to do privacy-preserving smart contracts, sort of in a general way, but they're very restricted in the compute that they can do. It's either going to be some kind of zero-knowledge proof or homomorphic encryption. They're very limited in the capabilities that they have, and they tend to be really bad in performance. So really, the computation with SGX, it gives you a little more than what you can do with other places, but it's really a general purpose programming environment, which makes it a lot simpler and a lot more efficient than the other techniques.
Do you, so how do you, at the moment, using this, you would effectively, the identity is defined by the device rather than the individual. Have you thought about how to verify an individual and attach them?
Yeah, so just let's separate here a little bit. That the only thing we really need the identity for is to verify the integrity of the computation. Right? We really don't care what the computation is. We just basically say, look, you gave us contract object input with a particular state, a particular version of state. We performed a computation on it, and the result of that computation generated a new version of state. And what goes on the ledger is just basically a hash of the old state, a hash of the operation was performed, and a hash of the new state. And so the hardware just basically says, these three hashes constitute a high integrity computation, right?
Right.
So the details of what happens in that computation is completely independent of that. So there's no reason, for example, why we couldn't hook in sovereign identities for individuals and define policies around that. There's no reason why we couldn't use X509 certs and cert verification in order to be able to represent the identity of devices and organizations. So while we don't take advantage specifically of the device identifier in the computations we're performing, we can take advantage of that is the contracts that we implement can take advantage of any identity system that you have available to you.
Okay, I think I'm there. There's still a step that I'm not quite clear on, but I get the. Is there once you created that sort of trusted, you use the triple hashing to create that trusted entity. How does the how does that get unraveled without access? How does that get operated on without uh, can it be calculated? Can the calculations be done on a different SGX platform?
Mm-hmm.
Right. So yep. There's nothing that's making that tied to that specific platform after it's done.
They're not tied to a specific server or a specific compute piece of compute. But you do need SGX someplace in order to be able to execute the method someplace else. So when we did the driver profile example, the profile for the driver, actually, the driver gets to decide where he wants to execute it. And so you can execute it on a laptop, you can execute it on an AWS server instance, well, in this case, Microsoft Azure. And it doesn't have to be anything close to where the insurance contracts would run. Right? The insurance company could provide those information. For other things that we're doing, again, it's the location of the execution is really independent of the contract, and you get to pick a little bit based on what you trust, right? On what your institutional trust is, but you get to pick where it executes.
Gotcha. Could you use this to create an identity service?
Mm-hmm. Yep, and in fact, that's one of the things that we've poked around with doing.
Okay.
So I can take, for example, an ECDSA public key and map that public key to characteristics of an organization that can then be verified.
Got it. Okay. That makes sense. Other questions, other folks?
Okay. Then let me just go ahead and finish up with this kind of more sort of smart cities example on this. And this is sort of the example that motivated us. We started working on this particular problem maybe 3-4 years ago, and we've gone through multiple solutions, including something that's effectively a zero knowledge proof based approach to this, and then we've done the private data objects version of it that way. And I live down in South Beaverton and Cooper Mountain area, and driving back and forth from Hillsborough, go through this Rosedale 209th intersection, and it backs up every single afternoon now. This is what happens when you put 3,000 extra homes out in that area.
Yeah. I've been on the other end of that debate, which is that somebody can't build buildings without doing massive modification to the junction, right? So it works in both directions.
I was going to say it's exactly that situation, and so so you've got this problem that this intersection is backed up, and there are two potential solutions for it, right? One is you go through and you just fix the intersection, right? Put a stoplight in or put a circle in, whatever the appropriate thing is, but because of the restrictions on access to land, the cost of that might be exceptionally high. If you know, for example, source and destination of the traffic, you might be able to, by making smaller changes to less expensive intersections, redirect the traffic away from this particular problematic intersection. And this is actually part of what they're actually trying to do in order to fix this problem. But in order to be able to do that analysis, you really need to know source and destination for cars that are going through the intersection, and that information is private. And getting that information from cars and from drivers in particular is a bit of a problem. Getting participation, verifying that the information that you're collecting is being used exclusively for this particular application, and that it will be thrown away when you're done with it. The trust relationships that are there are very, very difficult to manage that way. So our solution for this is basically come back and implement one of these smart contracts. So the Department of Transportation implements the contract. And that contract is going to manage all of this route data that's being collected from the drivers. So any driver, any individual can put route data into the contract. The contract allows that individual to remove their data at any point in time. The contract, so in addition to sort of providing these basic facilities and protecting drivers from seeing each other's information, it also protects the Department of Transportation from seeing the information. So even though the DOT owns the contract, the only operations that they're allowed to perform on that contract are what amounts to K-anonymous queries for us, but you can think of them as differentially private queries, which reflects essentially a heat map of source and destination through the specific intersection. So it gives them the information that they want, but there's no way in the world that they can actually identify the contributions of an individual driver to the results of the query that they're getting back. And of course, with the differentially private thing, we have to enforce sort of limitations on the number of queries that can be performed on the data per day. So the Department of Transportation is restricted on who, how many, and what are the kind of interactions that they can have with this data. So we have a means, this contract, in a sense, becomes a way to verify the integrity of the claims that the Department of Transportation is making. The driver data is always encrypted, so only the driver gets to know what data that they're contributing to it, and they can only see their own. Analysis happens through these smart contracts in the secure enclave, which means even when the analysis is being performed, the Department of Transportation doesn't get to see the information during the analysis. And one of the nice things about this approach is that we can remove the data and prove that we have removed the data. So we can prove to the driver that the data has been removed, but we can also prove to an external auditor who's coming in that the data has been removed. And then the nice thing about having these things as sort of an arbitrary smart contract development platform is we can add really cool bells and whistles onto this that are necessary in order to motivate drivers. So for example, we could do a whole token-based reward system that went along with providing your data to it, providing access to the data. This is the characteristics of having a very nice, sort of broadly programmable system for it. So just to sort of conclude then, the technology we've built allows us to do these sort of confidential computing to build these confidential computing applications on data. We can coordinate the action between a bunch of parties that really don't trust each other to do the right thing and trust that these contracts are going to be able to enforce the set of policies that we all agree to on data access and data updates that way. Code's available through Hyperledger Labs, so it's an Apache 2 license. We're currently defining contracts using a functional language that executes inside the enclave. We've got a number of samples for doing both the sort of driver profile stuff and the analysis that goes along with that. And of course, since we came out of the blockchain space, we must do smart contracts for asset management and fair exchange and payments and all the rest of the stuff. The code that we've done is largely independent of a particular distributed ledger. So we could just as easily use the IOTA backend for doing commits as what we're using right now with the Sawtooth. I think we've got Sawtooth and Ethereum support, and we're working with IBM on getting support for Fabric, for Hyperledger Fabric. And there's one more that's kind of in the work. And then on the contract interpreters, the future direction is really to support WASM, which would give us a very nice development environment that's cross-language for building the contracts.
I'm not familiar with WASM. What WASM is a
WASM is the web assembly language. Okay. So many of the applications that you're building for your browsers right now, what WASM gives you is a well-defined sandbox in which you can execute code. So you execute your code inside your browser code inside the WASM interpreter. It's completely sandboxed from the rest of your machine, so that this is how you get sort of secure download of applets that you're going to run in your browser for it. it's a very general execution environment. So we're taking advantage of that, or we'd like to. So.
Very, very interesting. That and the application you bring is very relevant. There's a lot of interest in doing something akin to this. A couple of questions there. So there's nothing that would stop you turning it around the other way and saying, let's say I by default on my phone turn on tracking and put all of the information about my location into a data store that is mine and is encoded to me, and that the digital contract only comes later when TriMet says we're thinking of planning a purple line from here to here. Would you share your data? Then we can agree to a contract that would come into my personal data store, identify that information and only that information.
Yep.
And provide that to the SGX to calculate, as you say, in the sort of K-normal kind of
K-anonymous, yeah.
Yes, K-anonymous kind of way.
And in fact, Wilf, that's pretty much exactly what we built for the driver profile piece for BMW.
Interesting. Okay. There's a lot of once you go that way, then for the smart city, the place that it would probably make sense to do this is that by default, your personal data store would collect a large amount of information.
Yep, exactly.
You basically just turn it on by default, and then in order for the city or service providers or others to gain access to that, they would ask you to agree to a digital contract that gave them the information they need to customize a service for you, and you could turn that off. So that's a fairly generalized model, right? That we should be making, within this framework, we should be making that approach as easy to program into all services as we possibly can.
Yeah, and that I think is the approach that we're primarily interested in taking as well for us. The one thing, depending on how, for example, how important integrity is of the data that's collected. So do I, in that data store that I collect about my locations, for example, making sure that I can't go in and manipulate that data. Frankly, I'd like to make sure that intersection at 209th and Rosedale gets fixed. So if I can go in and modify my data to show that it should be fixed in the way that I want to, that's not a good thing either. So there's this sort of mutual distrust here, and the data store that we create for ourselves has to be high integrity and has to have verifiable integrity as well for it to be useful in the analysis that someone might use it for. So all of these pieces sort of fit together in how we create different forms of computation on confidential data that way.
Yes, and there are a lot of other applications that are the same way, that you want to know that some entity has validated that data going in, right? That I assume in that particular case, it's the thing that's collecting the data that has to be valid. And when it puts it in, you're marking it and saying, this device put this data in here at this time, and it cannot be modified.
Right.
There's a lot of other places. I mean, the obvious one is bank account information, right? That I would like to be able to show you my bank balance, but if you can't look at my bank balance and know that it was actually put there by my bank, not by me, then it's not valid. It has no use. So, and there are a lot of situations where you want that. You want to be able to say, TriMet is giving me an incentive. So when TriMet checks it, they want to be sure that incentive is the incentive they gave and not a counterfeit of that incentive.
Yep.
So that's also a very general mechanism that we could lay out. Did you go through that exercise of sort of saying, okay, now we've done this for this traffic exercise, how would we generalize this so as this was a general mechanism, or is that sort of already built into the code that you've open sourced?
So the code that we've constructed is really intended to be a general purpose programming environment for this kind of application.
Right.
And then the example applications that we built on top of it, we have not really pushed for generalization of the APIs. Let me back up. We've pushed for generalization of the APIs for our immediate current constituents, which are all sort of in the financial services, asset management space. Right? So we have some very, very concrete notions of what constitutes escrow and exchange and fairness of exchange and confidentiality. So in that case, for that particular domain, we thought hard about it. But for the sort of personal data and sort of integrity of the data, we've got less information about how to generalize that.
Gotcha.
So really the right way to think about private data objects is that it's a programming environment for confidential computing applications.
Right. So one of the things we've been talking about a lot is how do you make sure that this is scalable from the technology, not just, you already talked about scalability from the point of view, hey, can I do billions of transactions this way?
Yeah.
And I get that, right? But there's also another issue here that that over time, if we establish a framework here, that over time, technologies will change. There will be many implementations. Cities will want flexibility to move things around. And I think you've sort of partially answered this, but I want to go there a little bit again. How does it interoperate with other things? You talked a bit about, for example, I could integrate an identity that came from Ethereum, and that would work in here. I want that kind of flexibility, not just temporarily now, but I can imagine a situation in which Intel comes up with a better than SGX kind of enclave mechanism and wants to be able to bring that into the environment and doesn't want to be, carrying a lot of legacy with old technology that went on. So does it build some sort of legacy in that these enclaves are sort of, they require SGX, and if they were stored for 10 years and Intel wasn't making an SGX processor anymore, that there would be an issue there, or is that not an issue?
So I'll give you a couple answers to that. One is we are trying to abstract out the layer at which we're trying to look for abstractions are sort of what are the characteristics of the compute environment with regards to confidentiality and confidentiality preservation. Right, so I want to be able to identify, and I'll just give you a concrete example, right? So if I get a virtual machine from AWS, from Amazon, its security and confidentiality characteristics are going to be very different than if I get some spare cycles from the grad lab at Stanford. My expectations for what people are going to do to that virtual machine and how it's going to be managed are very different. So we're trying to find ways to abstract out the representations of those. That allows us then to be kind of platform agnostic, or at least the policies for what constitutes your requirements for confidentiality can be expressed at a higher level. So AMD has this thing called SEV, which is an encrypted virtual machine. And this is a really cool thing. It does a really nice job. It does a very nice job of protecting you from other virtual machines that are executing on the same host. It doesn't protect you from the owner of the machine. But if you more or less trust the owner of the machine, then SEV would be a great way to implement this as well. So we're trying to come up with ways to abstract the sort of computational characteristics so that this becomes a very long-lived capability. Second answer to your question is the contracts are intended to incorporate policies for things like data aging. So what we talk about are ways in which there's a time span of 6 months over which no one's allowed to see this data. And at the end of the 6 months, the data can be anonymized and then made available, right? And our data objects can enforce a policy like that. We've talked a lot about how to write these long-term archival policies so that the contract decides what you should be able to do to it 10 years out. And so we're looking at those, the ledger operations have to be measured in decades. And so those are exactly the kind of problems that we're concerned with and trying to address. Right?
Oh, that's really interesting. I mean, the whole policy area of this, and what we're focused on, I think, here mostly right now is the mechanisms. But in building the mechanisms, we have to have some idea of what kinds of policy we want to implement to get the mechanisms right.
Exactly.
So that's been a bit of a chase. The one of the things that we've seen as being valuable here is this hierarchical nature of some of the contracts you want to write, right? So some contracts, are very common and require very little in the way of attestation or they can be done at a lighter weight level. Some, and we do this in our lives all the time, right? If I'm buying a house, then I have to behave very differently about identifying myself and giving information than I do if I'm getting on a TriNet vehicle.
Exactly.
And I do it with different and sort of cascading identities too, right? Some transactions I need to bring my passport to the table. Some I need to bring my birth certificate. Some I can bring a driver's license or just a letter that was mailed to me. And understanding that and using the right kinds of attestation and having them cascade. So if somebody is suspicious of the letter I brought in, they can say, "Oh, could you show me a driver's license?" Right? And that allows us in some way. So then you could think about things like SGX as fitting in there somewhere, right? Not necessarily being, that we're not requiring a particular kind of attestation or a particular kind, but we would probably want to qualify the level of attestation and the level of security of the transaction in a way that was relevant to the transaction that was being done. Does that make sense?
It makes perfect sense to me.
Yeah. But, so the work that you're doing here to try and get to the essence of what that means, I think is really helpful.
Okay, good.
Very cool. Other questions?
I will just make one request, is that most of our partners to date have been from sort of financial services, and so that's really where a lot of our concrete use cases have come from. A lot of the data ones are ones we've dealt with in the past, and we've got simple implementations of them. If anybody has a really good application that they want us to test, specifically related to sort of IoT related data, please get a hold of me. We'd love to talk. So
I suspect there are several here. We're also part of this group, Global City Teams Challenge, which is the NIST organization, and there are a number of cities. I think several of the things you talked about, we have people who are interested. Some of which right? There's obviously the ones like the farm to fork work that you guys have already done, Richard's done with Independence, Oregon, and that sort of is one class of these that I think is extremely interesting to do with freight and shipping and security on those paths. There's a lot going on in transportation at the moment, not just traffic planning, but incentivization of traffic behavior through various, as you talked about it, incentivizing people to share data, but actually the idea of incentivizing people, for example, not to bring their car downtown. And how do you tie those kinds of incentives into access of certain things, right?
Right.
That's a big issue at the moment. Actually, Portland's doing some innovative stuff in this space, and I'd love to talk about that in more detail. But I encourage others on the call here. I think a lot of the people on this call are more interested in the mechanisms, but there is another whole group of folks that we can tap into who might well be able to answer that question better for you, Nick, on the, bringing examples to the table. Jeff, I know you've been working fairly extensively across a lot of people working in the blockchain space, and particularly around some of the stuff with cities. Do you have anything here that Mick might be interested in?
Is that directed at Jeff Gals?
Yes, it is.
Oh, thanks. Yeah, Mick, the area that you talked on with the private data objects that's intriguing to me is when you talked about personal data property. And there's an initiative that I'm working on, and while you were talking, I was texting with the CEO of the company, and Wilf and Mick look for an intro on that later today.
Okay.
But there's this whole concept of controlling my data and determining who it gets released to, which you touched on. So I'm glad to see that Intel's working on that from the chip level now. And you said that you want to look for the application layer of that moving up. Yeah, there is something going on there. Let me just get permission from the guy to bring it to your attention. So look for a private conversation later today.
Okay, that sounds good. And I mean, one of the things, and Richard Beckwith and I have had several conversations about this. One of the things that we've been kind of looking at with data is that concept of ownership is really tough in this space. That what it really comes down to is different individuals have the right to perform different operations on some chunk of data. And it's more general than our sense of, owning a car is not quite the same as owning data. And so that we've been using the private data objects work to actually tickle out some of these sort of unique characteristics of what it means to own data in that space as well. So.
Yeah, and Mick, what's your email address?
I can put it in the chat as well, but it's mick.bowman@intel.com.
It's easy enough.
Yep. So I just posted it into the chat if you need to get a hold of me.
Thank you. Appreciate that.
Yeah, it's interesting, Mick, to think about. And I think the other thing that's complex about data ownership is that there's probably a cultural element to it as well, right? There's a societal element here that we have to address, and that was why I think the idea of separating the mechanisms from the policies, even though you need to know a collection of policies to know what mechanisms you have to put in place, the mechanisms should not dictate the policy, and they should allow different data ownership policies to be implemented, say, in Paris and New York and Beijing, because they probably will be implemented differently.
Completely agree.
Right.
Okay, well, one comment about that, Wilf, and then I have to bounce, Wilf and Mick, is that legislation that we have working through the Senate here in Oregon has teased out a very interesting opponent to the concept of personal data ownership, and it's none other than the American Civil Liberties Union, if you can believe that. What they're concerned about is that it's going to create a bifurcated society, which is the people who are wealthy will not need to sell their data or put their data into the marketplace, and it will compel poor people to slaves to the data organization or to the data marketplace.
Yeah, and the social implications for data ownership are really challenging. That would be a fun discussion to have. Ideas on that.
Yeah, it's up on their blog post if you're interested, because they're coming after one particular company for whatever reason. But yeah, I was very surprised at the ACLU coming out. Yeah.
Well, someone definitely should be raising it, right? There are issues here. I think what we need to make sure, though, is that those concerns get addressed in policy and they don't stop us building the mechanisms, right? That argument is a legitimate argument to have with the policymakers at the state of Oregon, right? About how that's managed. You don't want to remove the mechanisms for right? So it's sort of like, right, like, you know, we need the legal system. You may disagree with various issues associated with punishment and what's a crime, but you still know that you need the legal system. We need the mechanisms. We should make sure that we're, as technologists, not trying to decide what societally is correct, right? That should be up to the politicians.
Yeah, and I completely agree with you, Wolf. And I wouldn't even I would say it's up to whoever's writing the applications, whether the applications are being implemented in the context of politics or finance or sort of personal and social issues.
Right.
And that's really that's precisely the kind of programming environment we're trying to create here.
Yeah.
And this is my research group's long-term interest is in creating that programming infrastructure for exactly this class of applications.
Right.
Very cool. So I have to dash, but look for an intro in a little bit later today.
That'd be
Thanks.
great. Thanks.
Thanks, gentlemen. Take it easy.
Right. Take it easy. Have you seen, Mick, and along this line, a scripting language that would allow you to write digital contracts if you were not a technical person, right? Something that a lawyer could look at and say, I know what I've implemented in the digital contract. It's just a precise but understandable language. Have you had that conversation?
Yes, and I'm not sure that those contracting languages are an improvement. That is, you have to be a lawyer to read those. Read them. So you either got to be a technologist to read the code, or you got to be a lawyer to do it. And I will say that I think the most important thing is that the contract that we agree to has to be something that's public. The contract is transparent, so that others can review and observe what the characteristics are of that. So if it's coming out if it's using one of these sort of contract languages that are really designed for legal contracts, for executable legal contracts, then we need to have lawyers that can look at them. If it's a chunk of code, we need to have the coders able to look at it and review it. I don't see any way around that sort of social connection. Right? It's not. We talk about public policy. Public policy is printed so that we, as consumers of that policy, can go review it. Whether we do or not is another issue.
Right. I could see, as far as the city is concerned, most of these contracts are going to be heavily used, and so there'll be a lot of eyes on them. Right. That when you take ownership of a piece of land, right, it's going to be the same contract for everybody in Oregon, and it's going to be combed over, and everybody's going to have a pretty good idea of how it works. I think the place where it starts to get tricky is in these one-on-one type contract areas. But how you borrow a car, how you get an office space, how you get a piece of land, those contracts are typically going to have been well trodden. Right?
I really agree with you, and I guess the approach we've taken, and I'd love feedback on this. The approach we've taken is the data is private, but the contract is available for introspection between us, right? So we know what we've agreed to, or we can establish what we've agreed to, but the data that we're agreeing to is hidden. So,
yeah.
And like I said, I'd love feedback on it. That's a decision that we made that seemed like the right one. So
I think it is. I'm not sure I've thought through all of the places where it might make sense for that not to be the case, but I will mull on it, and if I come up with a strong one, I'll drop you a note.
Mm-hmm. Okay.
Hey, this was really helpful, Mick. Thank you. Really excellent, and thanks for this. I will get this posted for those who were not able to be on it, but a really helpful presentation. So thanks, and until next week. Yep. Thanks, everyone. Have a good one. Cheers.